Can you hear me? Can you hear me? Yeah. Okay, good. Okay. Thank you very much for coming and staying around for this late in the day. So I'm going to talk about some new work we've been doing. The work was mostly done with Claudio Spies, David Groh, and Yuvraj Virk. David's right there. Say hi, David. So if you have any questions about the work, you should ask him. Any mistakes in the work are probably, the presentation are probably my fault. Okay, so this talk is about what I call last mile headaches. So first let me define these first and last mile things, right? So what we in general have is a developer who's got some idea in her head, and so she turns it into a prompt and gives it to a language model. The language model produces some code, and inevitably this code is a nuisance, right? So there's a lot of stuff you have to do to actually make it work. So this kind of pair of things is what we call the first mile and the last mile, right? So so this last mile is a bit of a misnomer because it's not really the last mile, it's the beginning of the end of your life, right? So it's like there's a lot of stuff that happens after the code gets in. So when I was first learning to do software engineering, about 40-something years ago, the thing I heard was that like maintenance is 90% of the total cost of ownership of software. Now people say it's less, but still there is a lot, right? So whatever code that comes out of these language models that goes into the repo is going to be around for a long time, and you're going to have to take care of it, right? So this is the part that I'm actually, our group has kind of been thinking about these days, and we have some sort of interesting ideas, right? So what is about these maintenance costs? And how much are they? I've talked to people at various companies, and I can't get a straight answer on this, and it's very, very frustrating. I don't really know how people can continue to use these language models and not know what the actual total maintenance cost of ownership of this software is. So I think that's really aggravating. As an engineer, it's like, how can you do this, right? And yet they are, right? Okay, so this is a new post from Google. They're saying 25% of all new code at Google is generated by an AI. It's been going on for a while. So it's been a couple of years that they've been talking about things like Didact, where they're getting a lot of stuff generated. So there must be metrics and measurements starting to come in about how good this stuff is and how much aggravation it is to take care of it. Hopefully we'll start to see some of that soon. Hope springs eternal. All right, okay, so, just to give you data on, and I might sound like a terrible pessimist, just to give you the idea that it's just not being a grumpy old man, which I am. It's more than that, okay. So here's some experiments we did. This is using a few different models. This is work done by David Groh and other people, right? So essentially what we do is, for example, you try code completion. The idea is you give a prefix for a function which has test cases. The prefix is asking the language model to generate code, which may have gone in before the test cases went in. So the test cases are probably more mature than the code that actually went in, right? So we're asking to do code completion, and we're seeing if the test cases pass. Now bear in mind that the test cases are maybe sort of more retrospective, that they may know more than was known at the time the code was completed, right? Okay, so we get correctness around 30%, okay? I think this is an interesting number that's worth paying attention to, right? Because these test cases may be more mature than the code, and what you really want is long-term correctness in the code, right? So another data set, this is buggy fixed code. I'll say more about this in a minute. So in this case, we get correctness even less, but it's a harder case because here correctness is not just passing test cases, it's exact match with the code that's actually supposed to be the correct code, right? So it's a little harder to get it right because it's not just passing test cases. Okay, so of course, this is sort of a difficult setting, left to right completion. Fill in the middle, syntax error fill in the middle, may be a little easier, so maybe this is a little harsh. But this is what we get. Okay, so now let me talk about this simple stupid bugs. This is a wonderful data set from Sutton and Karampatsis, 2020. There's a whole MSR section dedicated to it. Single statement bug fixes, 17,000 examples after cleaning, collected from 1,000 projects. Median fix time about 4 days, but sometimes, and there's the rub, much longer than that. Okay, So, okay, so all samples in this data set were fixed before the language models we used were evaluated. What we're essentially going to do is to tell you what happened when we try to see what language models would do. Would they make the same simple one-line mistakes that programmers made? All right. So by the way, I invite clarification questions anytime. If you have issues with what I did and want to argue with me, please wait until the end. Okay. But if you have clarification questions, please ask right now. Okay. So I just want to make sure everybody gets this experiment right. So the methodology here, the paper's right there. You can scan it if you want to get a copy of the paper. So the question here is, does Codex repeat human mistakes? So using the same data set. So the idea is you go back in version history and find when this bug was introduced using git blame. Okay, and then use the prefix to the stub as prompt, and then you ask the LLM to generate the code, right? And you classify the resulting completion using exact match, because we don't have test cases. Is it a bug, a patch, or something else, right? Okay, so this is kind of the idea. So you give the prefix in the blue bit, and then the language model is going to either produce that bug or it's going to produce a fix. Okay, and then you see which one it does, right? So so that's kind of the what we're after, right? Okay, so the result is so here's sort of what comes up. It produces the patch that is the correct version of the code, 13.41% of the time. These are the cases where if you had used the language model, because nothing else is changing, you wouldn't have made the mistake, right? Okay, in 26% of the cases, it replicates the same bug that the human made, right? And in the rest of the cases, it produces something else, no match. So we couldn't examine all of them, right? Because there's thousands of them. We examined a reasonably statistically significant sample. And what we find is that out of the 60%, 54%, not out of total, but 54% of this, which is almost 90% of the no match cases, are rubbish. They won't even compile. You don't know what they are. The rest of them, it's 2.85% are patches and 2.1% are bugs, and the rest of the cases we're not sure. Okay. So the moral of the story, yes, we get a lot of bugs, right? So Codex produces fixed code, Codex produces buggy code twice as often, and the rest of the cases it produces something else. All right, okay, so this is the manual review, so I'll just skip ahead. Right, so the last thing I wanted to talk about with this data set that's kind of interesting before we get into what we've been up to lately, this is from MSR 2023, the paper that from last year. Okay, so one question we wanted to know is, we're using language model all the time, right? The damn thing sometimes makes mistakes, sometimes produces good code, right? Now, how can we figure out what the eventual maintenance ramifications of bad code or good code produced by the language model is, right? So we wanted to evaluate, supposing we had used the language model and it had stuck in bad code, what would happen, right? So the way we decided to go about evaluating this is that if the code produced by the model was buggy, how long did it stay in the history of the system, measured in commits, right? So the idea is that if it stays longer in the repo, as history is measured in commits, then maybe it was hard to find. We don't know for sure, because there may be other reasons why it's stuck around, because maybe nobody uses that code, right? But we just as a rough measure, we wanted to see what was going on, right? So when Codex made a mistake, did that bug stick around longer? So we can go back in history, ask Codex to complete the code, and see the cases where Codex produced the bug, see the cases where Codex produced the fix, see the cases where Codex produced something else, and see in which case how long that bug stuck around. Originally, it was a bug, because otherwise it wouldn't be in this data set, right? They're all bugs, but we wanted to see, of those bugs that Codex prefers to write, are they sticky? Is that question clear? Right. Okay. Yes?
Are you filling it in the middle, or are you giving it the context till the line and asking it to predict?
Left to right completion.
Left to right.
Yeah. Okay. So as you can see, the leftmost one is the bug. That's the case where Codex produced the bug. The middle case is where the Codex produced a patch, and the other case is where there was no match. And what we do find is that if Codex produces a bug, it sticks around longer. All right. So, and we do have some, it's unpublished yet, we do have some human subject study which suggests that if a bug is written in a more natural form, that is with lower entropy, then human beings have a harder time seeing it. right? So if the code looks natural and has lower entropy, then human beings have a longer time seeing it. So, I mean, I'm a grumpy guy, and this makes me even grumpier. I don't like this, right? Okay, so, you know, maybe this suggests that if a language model makes a mistake, it's going to take longer to fix it, right? Okay, this is a rather argumentative position, and I hope some of you will argue with me afterwards about this. All right, okay. So the point is that they're now widely used. I dare say they are ubiquitous in terms of programming practice. And is this code any good, right? You know, whoever came up with the idea of using language models for code, you know, beat them up. All right, so if this code is not always good, then what will happen? All right, okay. So the setup is this, right? So this is sort of, now we're getting into what research we've been doing and what we've been trying to do. We have this poor developer trying to use code produced by a language model, and you know, obviously it's parts of it are wrong, and the developer is faced with the struggle: should I accept this? Should I not? It seems to be nowadays they're mostly accepting it. There's a nice paper, maybe somebody remembers the title. It talks about these two modes of operation, acceleration and exploration. And in the acceleration mode, developers accept all the code very quickly, and in exploration mode, they tend to be more querying and interactive. So, you know, maybe this developer is taking this code, maybe they're not, they don't know, they're trying to figure out what to do, right? So, you know, you have this potentially incorrect code, and the question is, what should you do with it, right? So, what we're studying is this idea of calibration. The idea is that, like, there is this thermometer that comes along with the code that tells you how confident the language model is in the correctness of the code, right? Now, correctness has various definitions. So, you know, I think the most interesting definition is test cases that have lived for a while after the code was inserted, right? So that's the most interesting evaluation. So we'd like the language model to some sense be a prophet, you know, and when it's telling us, giving us the code, we'd like it to say, I'm 60% confident that this code in the long run is going to be good code, right? So that's what we want. We want a really good indication of correctness, right? And so this kind of indication, if we had it, allows the developer to make a rational decision. That is a decision with good outcomes in expectation, right? So a rational decision using this kind of confidence that's actually meaningful. All right, so how can they do that, right? So the idea is that the developer might say something like, I'm going to discard this code if the confidence is low, right? And this is a rational decision because if the confidence is low, maybe in the long run it's going to be more trouble than it's worth, so I might as well write it myself, right? If the confidence is high, then they might accept it because it's going to save them a lot of time immediately, and in the long run, it's probably going to be okay. So, you know, this is a good decision in the long run, right? And if the confidence is somewhere in the middle, the confidence is medium, they'll review and edit it. And again, they're making the right decision because they're spending some time now to avoid problems later, right? So this sort of rational decision making would be possible if this confidence in the thermometer over there was a good, reliable confidence, okay? So the rest of this talk, you know, will be about like, what does that mean to have a good, reliable confidence? So we need what we call a well-calibrated confidence, right? So what does this mean? Okay, so for this confidence to be allowing us to make rational decisions with highest value and expectation, whenever the output is generated at high confidence, it should be empirically correct, right? So the confidence in the model should correspond to the empirical correctness, right? If that's not the case, then the model is being overconfident, right? The model is telling you something is very good when it's really not. The model is being overconfident, right? So if that happens, then I'll be kind of using code without reviewing it carefully and giving myself higher cost in the long run, right? If the output is generated at low confidence, it should be wrong most often. Otherwise, the model is underconfident. If the model is underconfident, then I'm sort of not taking good advantage of the work that the model is doing for me, and I'm wasting time, right? So that also leads to higher values and expectation, right? So if the model is generating output at low confidence, it should be wrong most often, right? And somewhere in the middle, you know, it should be right and wrong about as much, because then I'm going to make good decisions about what I'm going to do with the thing. All right, okay. So these slides are made by David. Very, very nice slides. Unfortunately, the animation is lost in the PDF, so sorry, David. Okay, so, you know, predictive models, you know, many predictive models come out with probabilities, right? So for example, a rain prediction model might say probability of rain tomorrow would be 54%, which in California would cause most people to jump for joy. Maybe not here, right? So you might say that. And some other times they might say the probability of rain tomorrow is 36%, so you expect it to be sunny, right? So 54%, maybe you think it's going to rain, 36% it's going to be sunny, you think. Okay, so there are many, many predictions one might make with different probabilities, and there will be outcomes, right? So sometimes you have like 83% probability. I don't know how I can point at something, but I guess I can't. So in the top left-hand corner, for example, there's a sunny spot with 83% probability, but actually turned out to be sunny, right? They said they thought it was going to be 83% rain. Yes?
Full sun rain icons, but I wanted to kind of go back to a little bit of your sort of switch and bait and switch tactics, where you initially said that maybe what's important in generated code is maintainability, that is, ability to make changes and detect bugs, right, in the first case. And now somehow correctness is the main factor. So, I mean, is it, like you're talking about a completely different thing, or do you think they are somehow related? Because it seems like they might actually go in opposite.
I grant they may not be related, so I'm focusing on correctness for now.
Oh, okay.
Thank you for the point. Okay, so yeah, so the question was whether I'm talking about maintainability or correctness, and I realize it may be different things, but for the now I'm mostly talking about correctness. Okay, so we have these things, and then we have this collection of predictions where sometimes the model says high probability of rain, and it actually is sunny. Sometimes the model says low probability of rain, and it's actually going to rain, right? So we have all these predictions, and what we want for a model to be well calibrated is to come up with something like this, right? Where on the x-axis we have the confidence of the model, on the y-axis we have the actual correctness rate, right? And you notice that sometimes the model says it's very high confidence of rain, like 83% on the top right there, on the very top right, and it actually is sunny, right? But it doesn't happen very often. Even when the model says it's confident of rain, it's not very often that it's actually sunny. Likewise, when the model is very low confidence of rain, it doesn't rain very often, right? Most of the time it's sunny. So this is what we want from a well-calibrated model, okay? So, kind of what you can see is when it says it's 60, 70% confident, it actually empirically is going to rain about that time, right? And if you have something like this, then you can make rational decisions, right? So everybody clear so far, right? So the whole game of calibration is to sort of figure out how far away from this ideal is the actual model. If the model is very far from this ideal, then you're not going to have rational decisions with good outcomes and expectation, okay? So as Audrey pointed out, I'm focusing on this notion of correctness, right? So there are two kinds of notions of correctness that we're going to use.
I have a quick clarification question. How is calibration in that case very different from accuracy? Because if a model is accurate, if it says it's gonna rain and it rains most of the times, it is accurate, right? And how is calibration and accuracy different?
Right. So a model can be very accurate, right? So supposing it's saying it's like accurate 90% of the time, right? It may say it may always come with a confidence of 90% accuracy. It may say I'm always 90% accurate, right? So that's kind of the baseline of what you can be, accurate or not, right? In the 10% of the cases where it's wrong, that 90% probability is overconfident, right? So at whatever be your baseline accuracy, rate of accuracy, you can be well calibrated or it can be poorly calibrated, right? Yeah. So you'll see more about this. There's something called a baseline Brier score, reference Brier score, and you have to try to beat that, right? Okay. All right. Okay. Correctness is a complicated topic. What do you mean by correctness? So we're just taking two of them. One is exact matches provided correct code. The other thing we're going to look at is correctness modulo testing. Okay, and of course here also the question is which tests are you going to use to determine correctness, right? Okay, so there's also this notion of formal correctness, which we don't use. To my great amusement, I heard recently about a formally proven correct operating system where the code is 20% as long as the spec. So which is correct, the formal spec or the code? The code is 5 times smaller than the spec. So you can imagine which is more likely to have defects. Anyway, interesting, right? So confidence. There's different notions of confidence. One, the models themselves are probabilistic, so they will output probabilities with every token that they generate. So there's an intrinsic probability from the model. So if the model is producing 15 tokens for a code completion, you can take the average, somehow take a cumulative statistic, summary statistic of the 15 tokens and get a confidence measure, right? So we call that intrinsic probabilities because just getting it from the model. And there are other methods, we'll get into more of that in a minute. Okay, so the intrinsic probabilities, the easiest thing to understand. So LLMs generate tokens one at a time, each according to probability space of choices, right? So there's like, if you prompt a model with print hello, right? And these might be the tokens that it comes, that it generates after that initial prompt. And each of those tokens will have a confidence associated with it because that's just the way a lot of these models work. You can get probabilities from them for every token. Right? Some might be high, some might be low, but it gives you a sequence of probabilities. So intrinsic confidence for us is just calculated from these series of probabilities. You get the sequence, and then you summarize the sequence to get a per token average per token probability. You can do either geometric or arithmetic mean of these probabilities to get some intrinsic probability. Okay, right? Okay, so you can summarize all of that. All right, so the question is, like, once you have this probability in hand, how do you formalize this notion of being as close to this ideal as possible, right? So how close are we to this? All right, so calibration essentially is a constraint on a conditional probability, right? So what's the conditional probability? So the event we have in front of us is that the model is predicting with some probability pi, okay? So when the model predicts with probability pi, something happens. The model says, I'm confident in this code, where the average token confidence for me is 60%, right? Now, conditioned on that, there's an event that we're interested in. The event we're interested in is this code correct, right? So then the model is trying to predict for us correct code, right? So, but remember, the correctness notion we're interested in is not what occurred in the corpus. What we're interested in is code that passes test cases in this context, right? So is the model's prediction correct for us means is the code that's generated passing test cases, right? Okay, so if this value is also pi, then the model is well calibrated. So that's why you get this diagonal line, right? So we predict weather with the rain with a certain confidence, and empirically we get that same value, all right? So that's what we want, all right? So, more formally, this is how it's often written. The PM is probability as per the model. Given input x, the output is y hat, is predicted with probability pi. And then the actual output, the y without the hat, equal to y. If that happens, then the model's prediction is correct. And that probability should be pi. Okay? Sorry, it's a little confusing. Please ask if any of this is not clear. Okay? All right. So that's kind of the story that we're after, right? So then that's how we get this diagonal line, because the x-axis is this probability that we're conditioning on, and the y-axis is the probability of the event that is conditioned, that is the consequent event. Okay. Okay. So so this is what we're after, right? And so just to give you a couple of plots of this, so basically there's two plots. On the left-hand side is Codex doing what it's trained to do, which is predict the correct next token, right? And the model is, surprise, surprise, very well calibrated with respect to the task because that's what it's trained on, right? So, so on the right-hand side is a different setting of this, which is where we take the generated code and then we ask GPT-5 to tell us whether it believes the code is correct. Right? So we ask GPT-5 to generate code, and then we go back to GPT-5 and ask it whether the code is correct. Okay, so the two different plots. As you can guess, the one on the left is well calibrated, and the one on the right is not. Okay. So, all right, so I explained that already. So, on the left, you can see that, there is a bunch of predictions. So this plot is based on a bunch of experimental samples, right? Because the y-axis is all experimental, where it's all measured as a result of experiments. It's not probability values calculated a priori, right? It's empirically measured probability, right? So on the y-axis, we have a bunch of cases where the model gave us confidences between 0.2 and 0.3. This is an empirical number. How many ever cases the model decided it was that confident. That's the number we have there. And the y-axis is how many of those cases actually turn out to be correct tokens for that spot. okay? So in this case, it's well calibrated, right? Okay. So as you can see, we're getting around 30% correctness for cases where the confidence is between 20 and 30%. Okay. So in this case, we have examples of both underconfidence and overconfidence, right? So there's a bunch of predictions where this GPT 3.5 verbal reliability is between 0 and 0.1, but it's actually correct about 30% of the cases. So in these cases, the model is underconfident, right? Not good, because we're going to waste that code unnecessarily, right? And there are cases where the model is overconfident. It tells us that it's got probabilities between 0.9 and 10, and guess what? It's still around 30% correct. So, it's kind of like under and overconfident, more or less, kind of at random. It's not really right. The other thing I'll mention is that the size of these buckets is variable. It looks like it's constant, but it's not. Sometimes you'll have the model having most of its samples be in the overconfident range, and sometimes you'll have the model having most of its sample in the underconfident range. Questions so far? Yes?
Yeah, sorry, I might have missed this part, but how did you calculate the confidence of the whole output of the model rather than just single token?
Yeah, so the two plots are different. And the left-hand side is just simply whether the token is correct in that position, right, which the model is trained to do. On the right-hand side, we're evaluating whether the total string of tokens passes test cases.
That's for the correctness, right?
That's what we use for correctness, on the right-hand side.
But the confidence, how was the confidence calculated?
In this case, the confidence is asked by reflection. We go back to the model and say, how confident are you that this code is correct? And almost always outputs around the same, regardless of whether the code is right or not, just chooses something. Okay. Uniformly at random, apparently.
Is there a choice between using the generative outputs logics while decoding rather than just reflection?
Yes, I'll get into that in a minute. Yeah,
Thank you.
Absolutely, yeah. So this is just meant to give you sort of two extreme examples, right? Okay, all right, so now how do we actually measure the result of this, like how good it's actually performing, right? So there are different ways of doing it. This is sort of standard, and there's been some papers that you can see before ours. I'll give you a reference to our paper in a minute. So this is essentially for each bucket, right? So there's a bunch of buckets, right, grouped essentially by dividing the range of values from 0 to 1.0 into equal buckets. So there's a number of items in each bucket. So that's the size of each bucket, pi, and then we divide it by n. And we take the difference between the correct fraction in that bucket and the confidence in that bucket. Okay, so this is an empirical correctness measure, ECE. Smaller it is, the better, right? The smaller it is means the closer you are to the diagonal line, right? The problem with this is you can cheat by always giving the base rate as confidence, right? So if you always say the base rate, right? So if you know that you're always 30% correct, and you say your confidence is always 30%, then your probabilities, all your prompts, all your answers will occur in this range, and you'll be exactly 30% correct, right? So if you've been observing your model for a while, and you just give the base rate correctness as your confidence, you'll get a low ECE. So you can cheat, right? So it's not a perfect measure. So this is a better measure, the one below that. It's called the Breyer score. So the Breyer score basically is for every sample, you penalize the model for how wrong it is, right? So if it's overconfident, so in the first case, right, the prediction is wrong, but it's overconfident, you'll get penalized more, right? If the prediction is incorrect, if the output is correct, but the prediction is low confidence, you penalize it, right? So if it makes the right prediction but at low confidence, in other words, the model is underconfident, it gets penalized, right? So you just simply summarize these probabilities, this penalization over all the samples. You square it to get a positive value, and then that's your Breyer score, right? And so this is basically also the same thing, like the smaller it is, the better it is, right? So now the reference score, I won't go into the calculation, you can calculate this. So if you try to cheat as before, right? In other words, you always give it the base rate probability. This is the reference score you get. So in the example, the question you asked, if you're 90% correct, the Breyer score would be 0.9 times 0.1, 0.09, right? So the reference score will be smaller the more biased the sample is, right? So if you have very low positive rate or very low negative rate, and you just use the base rate, this will be smaller, right? So really what we want is a way of comparing these two, right? So, so that's the skill score. This is the skill score. It's a reference score minus the actual score divided by the reference score. Okay, so just to give you an idea of what this is, right? So by the way, none of this is our work. It's just all old stuff that we're using in this setting. So if you always predict the base rate, it's called unskilled, so you get 0. You get no credit for predicting the base rate, right? The German Weather Service, which I can speak from personal experience, having spent 9 months in Germany last year, is pretty good. Their skill score is 0.07 predicting rain. Okay, so I could rely on them to decide when to take an umbrella or when to take a raincoat or when to take a bus, right? So it was pretty reliable. The 538, which is an American prediction company, I don't know if Canadians probably may not have heard of it. It's a very popular American statistical prediction company. Their prediction score for National Basketball Association is quite good. Mostly the betting markets will reflect this immediately, what they predict, because the betting markets trust them. Their skill score for predicting congressional elections versus coin flip is very high. This means almost nothing because in the US, the Congress people choose their voters, not the other way around. So this is very easy to predict in most cases. So now, here's the first punchline. Out of the box, the question you asked, the intrinsic probabilities in the language model are negative scale. You don't want to use them. Okay. This is our paper that's going to appear in next year's ICSI. Feel free to scan the QR code. The rest of the results are kind of from this paper. Right. Okay. All right. Okay. So we use these data sets: human eval MBPP for function synthesis, DIPI-bench for line level completion. DIPI-bench is a very nice data set from Michael Pradel in Stuttgart. Essentially, it's line level completions with functions that you can use that you can run test cases on. Defects for J is very commonly used. So in every one of these data sets, I've also listed the correctness measure. For human eval and MBPP, there are test cases. For DIPI-bench, there's test cases. For defects for J, use exact match. And for many steps for J, use exact match. Okay, so now we need a confidence score also in addition to the correctness measure. So we used average token probability, sequence probability, verbalized self-evaluation, and question answering logic. I'll explain all these in a bit more. And we used both the Breyer skill score and ECE. I don't like the function synthesis. I don't think they tell us much about how the model should be used in actual programming setting, because they're like small Mickey Mouse problems that no programmer would ever write. So I don't like them, but it's included mostly for completion. The DIPI-bench data set I think is much more realistic. Has functions with doc strings and running test cases. Okay. SWJ doesn't have test cases, it's only exact match. All right, so this is sort of the baseline correctness. So you can see, generally GPT 3.5 seems to do better in all pass. All pass is somewhat higher than exact match. You can imagine why, because exact match is more restrictive. All pass test case passing allows for more ways of writing the same code. So that's kind of the base rate. So for example, all pass at 1 Breyer reference score for DIPI-bench, it's 33%, right? So if you just simply guessed the same confidence for every output, which is 0.33, then you end up with a reference Breyer score of 0.22. Okay. Right, and so your goal would be to get under that if you can. Okay, so this is per token probability. Empirical correctness estimate is 0.15. Breyer score actual is 0.41. So this is if you actually calculate the Breyer score from the confidence. The reference Breyer score, as I said before, is 0.22. So we have a negative skill score. In other words, don't use the probabilities from the language model. It's worse than useless. And unfortunately, to my knowledge, this is often used to decide whether to show a completion or not. Okay, so the first thing I just wanted to mention is this simple idea called Platt scaling, which is, if you have some data of correctness, the relationship of correctness and confidence from the language model. There's two variables. There's correctness value and there's a confidence value, right? Two values. You can hopefully just simply fit a regression score, right? So the response is actual correctness, the predictor is the model confidence. 2 plus scaling value plus bias, just a logistic regression, right? So if you fit it, you can get like different curves depending on the situation, right? And then, you can just do this for rescaling. And so, so if you do this, you get a positive skill score, already somewhat better than the German Weather Service. So, so that's kind of a simple fix, right? We can do much better than this. So, for example, we can do what we call a verbalized self-ask. Ask the model, given its own code, to output a probability of correctness. And this reflective true-false logic. Ask the model whether its own response is correct. Ask it to output true or false in response to whether it's correct or not. And then take the logistic probability of the true normalized with false. Okay? And then the same as these things, but we can use few shots. Okay? And then we can do few shots both with retrieval augmented generation and random few shot selection. Okay? So reflective verbalized self-ask looks like this. So we have a description of the code in the double, triple quotes. And then we have some examples, and then we have the generated code, and then we ask for a well-calibrated % probability that this code is correct, and prompt it with probability colon, and the model outputs a probability, right? So that's sort of the last question answer bit. That's what that looks like. The reflective self-ask is same setup, and then the question at the end is true or false. This code matches intent and is bug-free, and you take the true, and then you take the logit with respect to the false. Okay, so so intrinsic is somewhat decent after rescaling. Verbalized self-ask is not much better. True-false logic is not much better. Few shot with true-false logic is the best performing, and so that's this score, right? So what you see here is if you use the true-false logic with few shot BM25, we get a skill score of 15%, which is actually really good and almost at the point where it's usable, right? Pretty much, you could probably put this into a prompting engine, and you will get pretty good reliable scores. So that's what that looks like. Just to explain this plot, the top plot is the same kind of reliability diagram that we saw before. The numbers in there are the number of samples that occur in each category. And the bottom plot is a histogram which shows you the number of samples that occur in each probability range. As you'll notice, the model is generally not very confident, right? Most of the samples are like in the below 0.5. Above 0.5, there's not that many samples, right? So this is for all the code completions it's tried. And this is appropriate. The model should be underconfident because it's bloody well wrong most of the time, right? So this is right. This is exactly what we want. Okay, so all right. So now the question is like, how do you present this confidence? I'll be stopping in a few minutes. Okay. So there's a couple of like different ways. You could color the completion in red or blue depending on how confident you are. In future work, we're doing actually, David's been doing some very interesting work to get very well calibrated token level confidences. If we have that, for example, in this case, we might say we're confident in most of it that number 7 might be different, right? Which is actually quite useful. It reduces the editing effort. So anyway, so this is the summary of the work. The last mile is extremely challenging, and we're hypothesizing that more information would lead to better outcomes, and we're arguing that well-calibrated confidences are possible, and we really wanted to user studies to see how these confidences might be used. I think there's some very good user study work to be done there, and we're happy to get some collaborators to do this kind of work. So I guess I'll stop there now. I have a few more slides, but I don't know if there's time on it. Okay, yeah.
Thanks for the great talk.
So Prem, there's some work from the ML community as well, which kind of says there's this self-love problem that these models have. If you ask the model whether the output that it generated is correct, it always kind of says, oh, I'm always correct in what I'm predicting, and has the self-love problem. And then there was follow-up studies that came in and said, yes, there is self-love problem, but that self-love is no worse than what humans have in their own confidence. right? Like humans saying that they're confident about something is about the same error rate as what these models have as well, especially when it comes to the same exact task, right? Like here you have humans predicting like the weather with models and other things with tools, but just asking humans, it's about the same thing. So do you think that would be an interesting thing to see whether, you know, maybe buggy code pre-model, pre-LLMs are going in because humans are very confident about their code and that these things might have a better skill level than humans and therefore it might be okay. I don't know. It's a hypothesis, right? So.
Yeah, I mean, so it's a couple of things in response to that. One thing I would say is you can't train humans to be appropriately confident, not under or over. We can do that with language models. That's one thing. The second thing I would say is I think the study would be very interesting to see whether human confidence is correlated with language model confidence, intrinsic confidence, and like why that is, and if there's a way to modify the human confidence and a way to modify the language model confidence in similar ways. That would be very interesting, I think.
Yeah, I think it's thanks for a very interesting talk. So I actually have two questions. So the first one is I see you are showing the result for pass set 1. So I assume you take the greedy approach, get the highest probable token, get the probability and so on. But in kind of, many of these kind of code generation solution now, what they do is they generate a bunch, like 5 or 10 of them, and they use one of the additional AI models to pick, what they think is the best, and then they go with that instead. So it's generally, let's say, pass at 5 or pass at 10 and so on. I guess my first question is, if we apply this kind of thing in that kind of multi-solution kind of context, do you think the result would actually look different because, because if they generate multiple, then they are not taking the greedy or the highest probability token as a result?
So what you're saying, the setting you're saying is like, for example, in DiPyBench, you ask for 6 completions from one model or many models? And then
for one model. So for example, let's say AlphaCodium, which they have a paper saying it's better than the Google AlphaCode 2. What they do is, it's coding competition, by the way. So for that particular thing, they ask them to generate 20 solutions and so on. And then based on that, they basically pick which one is better and so on.
Yeah, so there's 2 questions. One question is it correct? And the other question is the model appropriately confident?
Yeah.
Right, so you have to look at both. I don't know whether if you take multiple votes, the model is well calibrated. There's some experiments going on. David's doing some experiments on this, but I think that's TBD. But correctness may increase, no question. But I don't know if calibration will increase. I don't know if that paper discussed calibration in that sense.
No, they did not. That's why I was wondering. Actually, leads to the second question, is because because of the old one, now people are actually thinking about the newer paradigm, which is the test time compute. So it's follow along that line of workflow is like you're trying to search, or first propose multiple solutions, search among them, evaluate, pick the best one, and maybe kind of reiterate based on that and so on. So there's going to be some kind of evaluation. And currently the evaluation is actually another model, like an independent eye, looking at the things, say which one is good and so on. But this way is actually directly the opposite. It was the same model trying to assess their own solution, right?
Right.
So I'm just curious to see why you think it's better to have the same model give you how they think instead of have like an independent eye, for example, as human, to assess, how good they are and so on.
I don't know. I don't have a good answer for that. I think it's a good question. Whether if you reflectively ask another model, will it be calibrated? David, did we try that, asking a different model to see if another model's reflective evaluation is better calibrated?
No, I don't think we tried alternative models, but yeah, that's something we.
Yeah, it's a reasonable question.
Because so there was one thing, at least for the AI community, they think the judge or the reviewer needs to be a different model. Is sometimes there's something called reward hacking. So they may just kind of always give the good one because that's how they kind of getting the reward or think they are actually doing the good job.
Mhm.
But I'm just curious to see, because you're doing this calibration, right? So how, like, are they complementing with each other, or what's kind of relation?
I think it's worth trying, but we haven't.
It's related. My feeling is, I don't remember where I've seen, but there's like real evidence that these models try to be very positive. So you really need to ask questions in a way that, so basically it's giving the maximum, just trying to be positive and, it's reinforcing, and so it gives good confidence just because the model has been, pre-trained that way. So I forgot what the techniques are, but there are techniques to get around that by relative ranking, for example, or something like that. Like, are you more confident in this solution than that solution, and so forth. But I've heard this in some other context. I'm not sure if it's useful.
Yeah, we're trying various things. There's a bunch of prior work on getting better calibration. So this is the first thing we tried, I should say we're not the first to do this. There was a paper previously in ICSI about this topic. I think in some ways what we do is probably a little more stable because we don't use ECE, we use prior skill score. But anyway, so there is more stuff we're trying to make it better.
Tying it back to like the motivation of your presentation here with like long-term maintenance, I agree with you, right? Like I talked to CTOs and VP of engineerings in companies, and I'm scared when they say, "Oh, we just use all of it," and then we don't actually check whether this thing is any good later on. And now because they're doing 25% more, they're actually producing 25% more code. So there's more code for them to actually look through maintain as well, right? Not just the maintenance problems regularly. But there is can you evaluate how good these calibrations are without looking at it in a long-term view, right? Like, yes, the calibration score was high, and I accepted it. And then now 2 years later, I found like something that just ground my product to a halt, like a severity 1 bug that came up, right? And without knowing that 2-year span, would we know whether the confidence scores are?
So the experiments we've done is because of the fact that we use test cases that presumably were added well after the code was added, it gets at that, but it really doesn't. What you really need is somebody to just actually track which code they're adding is from the language model over a period of a year or 2 years, and assess whether the maintenance cost of that code is, minus the extra maintenance cost of that code, minus the cost of saved by adding the thing, is good enough that you're getting ROI on the language models, right?
I think that among the people that I've talked, there's 2 camps. One camp that firmly believes there's a very high ROI, and they use this. And then the other camp who believe that this is terrible and they will never use it because they're worried that they're going to have this huge cost later on. And neither of them have evidence.
Yeah, they're both ideologues, right? I mean,
yeah.
they're not. So I mean, I think there's a lot of good ESC empirical software engineering work to be done here. And we know how to do it, and we should do it. Yeah.
Maybe we have time for one more question.
Very nice presentation. I was just curious in terms of like whether these generalizes, right? So I think you evaluated GPT 3.5.
Yeah.
Have you checked other models if you obtain like similar calibration scores and stuff?
David is probably better positioned to answer, but I don't think we've done anything. We haven't updated this.
We did several models at the time, but obviously there's new models every
right.
whatever, so not. Yeah.
Okay, yeah, I just wanted to I guess the thing behind my question is I wonder if over time things are getting better or worse in terms of calibration.
It depends on the training, right? So I mean, I don't know that these models are being trained on their correctness, right? So if they're somehow explicitly trained to produce correct code, yes. The only extent to which they're trained to produce better code is the extent to which the code in the corpus is getting better. Or maybe they're using better curriculum, I don't know. Yeah. So I don't really know that. I don't have a good answer for it. I mean, it would be interesting to try the latest and greatest models to see how they do it. The other problem is, that they'll probably know this data set by now. So
Well, let's thank Prem for a great talk.